All right, so in this video, I'm going to briefly teach you how to graph the greatest integer function, also known as the floor function, and I'll explain what it means. And so this is the notation. There's three versions of this notation. Basically, it looks like there's some kind of variable inside a set of brackets with a set of vertical lines, or you can use just a single bracket, or sometimes they have an L and a backwards L. Now, your book uses this notation, so we'll just stick with this. Okay, so when you read this, this is the greatest integer function. And the definition of the greatest integer function is the greatest integer less than or equal to x. Okay, so whenever you plug into this function, think of what's the greatest integer less than or equal to what you just plugged in. We'll talk about what that means in a second here. And just recall, right, your integers are basically your counting numbers that could be positive or negative. It could be zero, but they're just not fractions. Okay, so let's start with an example here. Graph your greatest integer function, state the domain and range. Okay, so what I'm going to do is I'm going to just simply plug in some points. Okay, so -2. So if I plug in -2, and as soon as I plug it into this, funky double bracket, if you will, you got to think, what is the greatest integer less than or equal to -2? Remember, it has to be integer and it has to be less than or equal to -2. Well, if you think about it, right, the greatest integer less than or equal to -2 is just -2. So there's 1 point right there. Let's go a little bit smaller. Okay, or sorry, let's get bigger in value. What if I plug in -1.9? F of -1.9, what is that? Okay, so again, you have to think the greatest integer less than or equal to -1.9, right? Smaller than -1.9, and it has to be an integer. Well, a smaller number than -1.9 that's an integer would also be -2, right? And so forth, right? You can keep going. You can plug in -1.5. -1.5. What is the greatest integer less than or equal to, okay, smaller than -1.5? It has to be an integer, and the number that's smaller than -1.5 that's an integer is -2, the greatest integer, right? -2. Okay, so you can kind of just keep going, right, all the way down, -1.1, the greatest integer less than or equal to -1.1 is also -2, until we reach the value of the next integer, which is -1, right? If we reach -1, the greatest integer less than or equal to -1, it could be equal to it, right, is -1, okay? And then, let's get a little bit bigger here. What if we plug in, -0.5? Greatest integer less than or equal to -0.5 is also going to be -1, right? F of -0.5, plug it in here. The biggest number, the greatest integer that's less than -0.5 is -1. And then we can just keep going here. Okay, so let's go all the way down to, -0.01, right? The greatest integer less than or equal to -0.01 is still going to be -1 until you reach the value of 0, right? That's when your y value starts changing. So the greatest integer less than or equal to 0, right? If I round it down, is going to be 0, okay? Greatest integer less than or equal to 0.5 is still going to be 0. Greatest integer less than or equal to 0.9, that's going to be 0, right? And then you can keep going. So what I want you to notice right now is a pattern. The set of x values from here to here, right, such that the y value is still going to be the same, is from x is greater than or equal to -2, but less than -1, right? And when my y value starts changing is when I plug in the next integer. So this represents the set of x such that x is greater than or equal to -1, but less than 0, right? And over here, this will be the set of x that's greater than or equal to 0, right? Because the greatest integer less than or equal to 0 is 0, until I reach the value of 1. Why? Because once I plug in 1, right, the greatest integer less than or equal to 1 is just 1, right? So this next set, you could just keep going. X is greater than or equal to 1, but less than or equal to 2, right? 1.5, I round it down, that's 1. If I plug in 1.999, that's going to round it down to 1. Okay, so that's enough point plugging. What does your graph actually look like? This is called actually a step function. So let's draw some tick marks here. Okay, so between -2 and -1, which is right here, I have a y value of -2, but this guy right here is closed. And this guy right here, right, until I reach the value of -1, is going to be open. And then for this set of points, from -1 to 0, I have a value of, oh, excuse me, I plotted this wrong. Let me erase this. Okay, let's try that again. Between -2 and -1, the y value is going to be -2, right? So over here, it's going to look something like this. And it's going to be an open circle. Oops, this is -2, this is -1, -1, -2. Just label it here. Okay, so my next set of points, right, is from -1 to 0. And this is going to look exactly the same. It's going to be a closed circle here, right? Because at -1, you have this value of -1. And you have a bunch of decimal values in between, right? And you just draw a straight line and then an open circle at 0. Because at 0, you have the next point, which is this. So again, I didn't draw this perfectly, but you get the idea, right? And then from 1 to 2, you're going to have y values of 1, but it's going to be an open circle each time at the right. And you can keep going. The graph just continues on forever and ever. Okay, that's all there is to it. The greatest integer function. The domain, right, if you think about it, you can plug in anything for your x. The domain's going to be all real. And, you know, what is the range, right? What are all these y values right here? This is your range. The range is just the set of all integers, right? That's the point of the greatest integer function. Okay, so that's what I would do when I graph my homework, is just to plug in a bunch of points. Okay, but let's take a look at one example, because this is the parent function. F of x is equal to the greatest integer function. Let's take a look at one more example. How about if we graph f of x is equal to the greatest integer function of 3x plus 1. Okay, so in the next section of 1.4, we're actually going to go over transformation. And so later on, you will learn that this is a horizontal shrink, okay, by factor of 1/3. And this last value right here, right, it actually shifts it up 1 unit. Okay, but that's in 1.4. In this section, we're just going to plug in points. Okay, so just like I did on the previous problem, let's start plugging in some points. Okay, so let's start with 0. You know, if I plug in 0, I'm going to get the greatest integer. If I plug in 0 over here, 3 times 0 is 0. The greatest integer less than or equal to 0 is just 0. 0 plus 1 is 1. What if I plug in 1/10? Okay, I'm going to use a fraction over here. If I plug in 1/10, right, the greatest integer less than or equal to 3/10. If I draw those double brackets, right, the greatest integer less than or equal to 3/10 is just going to be 0, right? So you're going to have 0 plus 1, which is 1. Okay, now if I keep plugging in, let's just keep going. Let's say I plug in 2/10. Okay, f of 2/10. The greatest integer less than or equal to 2/10, or 1/5, right? Again, it rounds it down to 0. You're still going to get a value of 1. Okay, so at this point, you're like, is there some kind of pattern over here, right? Or do I have to keep on plugging in points? Well, what if I plug in 1/3? What if I plug in 1/3? F of 1/3. So if I do 3 times 1/3, I'm going to get a value of 1. And that is going to how, this is the point where it's going to start changing the y values, right? So the greatest integer less than or equal to 1 is 1. 1 plus 1 is 2. Okay, so what is the pattern over here? Like I developed a pattern in my last problem, right? X is between, -1 and -2, right? X is between 0, -1, 0 and 1, right? The difference between these units is 1 unit, right? 1 unit. Between this x value and this x value is 1 unit, and so forth. Well, do I just go 1 unit from here to here? Not quite. The way you figure out how many units you go, right, is you take a look over here. I went from 0 all the way until I reached the value of 1/3, right? So actually, this is the x value between 0 and 1/3. So any x value that you plug in between 0 and 1/3, you will get an output of value of 1, right? So if you can follow the pattern, right, the next one is going to be, this is going to be defined for the set of, if this is a difference of 1/3 units, I just take 1/3 and then I add another 1/3. So this is going to be 2/3. So if you don't believe me, let's plug in another value. I know this is all in fractions, so might be harder to think. A number that's bigger than 0.33 is 0.44, right? In other words, 2/5. So same thing. If I plug it in, 2/5 times 3, you'll get 6/5, right? And if you round this down, 1 plus 1, you're still going to get 2. So if I plug in 2/5, I'm going to get a value of 2. But what happens if I plug in 2/3, right? I said this would be the next boundary point before the y value changes. What if I plug in 2/3? Well, if I plug in 2/3, right, 3 times 2/3, that's going to cancel. The greatest integer less than or equal to 2 is 2. Right? At that point, my y value changes, okay? And so the difference is going to be 1/3 units. And so if I ask you, what's the next set of points such that the y value is going to be 3, it's going to be between 2/3, right? Oops, this should not be closed. This should be open. 2/3, you add 1/3 to it, which is just going to be 1. Okay? And the way you figure that out, right, in general, is that it goes up in increments, okay, of, let's say this is, let's say this is bx, okay, it goes up in increments of what? Or units, or you can think of units, right, of of x divided by b, okay? So in this case, it goes up in increments of 1/b. Actually, I should say 1/b. Goes up in increments of 1/b. That's how you figure out how many units. Because there's a b over here, in this case, my b is 3. So it goes up in increments of 1/3 for my set of x values. So you don't have to keep on plugging in points. Okay, so once you see the pattern, let's graph this. It's going to look something like this. So I'm going to have 0. I'm going to have 1/3. I'm going to have 2/3. I have -1/3, right? So what did we say over here? So 0 to 1/3, it's just going to be 1. So from 0 to 1/3, it's going to be 1. Remember, close on the left, open on the right. And then from 1/3 to 2/3, it's going to be at 2. Okay, and then even though I didn't plug in points between 0 and -1/3, right, you can see what the pattern is going to be. From -1/3 to 0, right, it's going to be closed over here, it's going to be open over here, and then you just keep on drawing it. Okay, so maybe I would ask you to draw maybe 3 of these steps on a particular problem on your quiz or test. Okay, all right, so your homework is also going to ask you to verify this using a graphing utility, and all you have to do is go to Desmos. And so let me show you how to do that. So Desmos. And the floor function for Desmos is just simply, you just have to type in the word floor, okay? So if I want to if I want to graph the floor, greatest integer of 3x plus 1, I would type in floor, and then I would use the parenthesis symbol, 3, enter the x right here, okay? And then you add 1. Where's my add button? Here it is, add 1. Okay, notice that's exactly what the graph looks like. The only thing that your graph does not do for you, right, if you scroll over, is it doesn't show the open circle right here. Remember, this is an open circle, right, on the far right. This guy right here should be open. So Desmos actually does not do a good job of showing that. This should be 0, 1/3, comma, 2. But at the 1/3, comma, 2, right, this guy right here should be undefined, okay? So this is how you basically graph using Desmos. You enter the floor function and just realize each points here on the right should be undefined, but they're not. So just something to be aware of, but that's how you graph greatest integer function by hand.